In this lesson, I'm going to talk about gateways, and in particular, default gateways. So what's a gateway? Okay, a gateway, as the word implies, is a way for traffic to leave one local network and be forwarded to other remote networks. So basically, think about the default gateway as the door out of the room. Okay, the room that I'm in right now, if I want to go out to the hallway, I'm going to have to exit through the door. When a computer wants to send a message off of its same local network, it needs to also exit its local network and to go out and be forwarded to the actual destination. As we learned earlier, computers figure out whether or not the destination is on their same local network by going through a process of binary ANDing, which takes the subnet mask and ANDs it with the destination IP address to determine if the network portion of the address is exactly the same as the network portion of the sending host. So in the case of where that is not true, the computer has to actually send the packet to the gateway. We learned that every host on a network has to have, at the very minimum, an IP address and a subnet mask. Now, if that host intends on speaking to destinations that are not on its local network, it also has to be configured with the address of its default gateway. Usually in today's network, the default gateway configured on a device is the router interface that the traffic would come to first on its path to the internet. So basically, if we were to look at me over here in the network management department, and if I was trying to reach a server that was out on the internet, my traffic would basically travel up through my switch, and it would end up at the address assigned to the interface, router interface, closest to me on the path to the internet. Now, if we go to a different host, say for example this one in the accounting department, and they were trying to reach the exact same server, their traffic would travel again through their switch, but they would enter the router at a different router interface. So the default gateway configured on hosts in the accounting department is different than my default gateway configured in my network management department. Once the host determines that the address of the destination is not on its same local network, what it does is it ARPs for the MAC address of the default gateway. Now this is important to remember because one of the problems that you find in networks frequently is because there's a mistake made, the default gateway address is not on the same local network. For example, if I accidentally configured this with 11 instead of 1, my computer would not be able to send traffic using ARP to its default gateway address. So we have to be very careful when we are configuring network settings that we have the correct IP address, the correct subnet mask, so that my computer can accurately predict who is on its own local network and who is off the local network located on a remote network, and the default gateway address so that it knows what router to send traffic to in order to go off of its own local network. In this lesson, we're going to talk about private IP networks and the need for network address translation when we go from a privately addressed network to a publicly addressed network. IPv4 addresses have two categories. The first one is private addressing. Private addressing is addresses that can be used within an organization. They work perfectly well. You can assign them to hosts. They can be routed between different networks. But when you need to go outside of your organization across the publicly addressed internet, you have to have a registered public IP address. Now, the people who designed IP reserved certain networks that you could use them within your enterprise, but they will not route across the internet. Those addresses are 192.168, 172.16, and 10. Now, most of you who have a home network, if you look at what the IP addresses are that are assigned to your various devices, you will find that usually they are assigned to the 192.168 network. The reason being is that it uses a subnet mask of 24 bits, which only leaves 8 bits for host addressing. Those 8 bits only have 254 possible host addresses. So they're used for smaller organizations and smaller networks. 172.16 now uses 16 bits as identifying the network portion, so you can have many more. And 10, it only uses 8 bits for the network portion, so it's used primarily for very large enterprises. Now, if we have a network addressed with private addressing, as we do in our little organization here, we would have difficulty sending this traffic out to a server that is located on the internet. The internet will only route registered public IP addresses. So 192.168 does not fall into that category. So a function was developed called network address translation. In network address translation, a private addressed host can actually send traffic across the internet. And the manner in which it does this is that the router, and you can see here is our router that connects us to the internet and also to our 2 privately addressed networks. The router performs a function that keeps a table in which 192.168 2.1 is actually represented on the internet with a publicly registered address. And we'll say that it's in the same network here, so it's 200, 100, 58, 50. And then if my host here decides also to communicate with a device out on the internet, it would be added in the table and assigned another registered address. So to hosts out on the internet, I am represented by this registered address. So when my packet goes out my network, so it leaves me, when it comes up here, the source address is my privately assigned address, 192.168 1.15, and the destination address in my packet would be the 210.100.5 address of the destination server. When it comes up here, the router looks at its network address translation table and sees that I will be represented on the internet by this address. So it changes the packet, my little packet here. When it leaves, the packet then looks like the source address of 200.100.58.51 and the destination address of 210.100.5.5. So when the packet actually reaches the server will send its response back to my registered address that was assigned to me here. So it'll address its packet with the source 210.100.5.5 and the destination address of my registered address 200.100.58.51. This packet will make its way back to my router, and my router will see 200.100.58.51, and it will say, who has that address assigned to it? And it will look in its table, and it will see that that address is assigned to me. So it will change the packet back to show my local address as being the destination. And then it will forward it back out to me. So I will happily get the packet from the server and be able to display the web page.
IPv4 addresses are 32-bit addresses, and IPv6 addresses are 128-bit addresses. But typically, IPv4 addresses are represented in dotted decimal notation, and IPv6 addresses are represented by colon-separated hexadecimal notation. The difference between decimal, hexadecimal, and binary is that the decimal number system is base 10, having 10 numbers 0 through 9. The hexadecimal number system is base 16, having numbers 0 through 9 plus A, B, C, D, E, and F, which stand for 10, 11, 12, 13, 14, and 15, respectively. The binary number system is base 2, having only 2 numbers, 0 or 1. So when we say that the IPv4 address is a 32-bit address, and an IPv6 address is a 128-bit address, we need to first convert the addresses to binary. You can see here that the IPv4 address 192.168.1.100 has been converted to binary, and we have 32 ones and zeros. The IPv6 address has also been converted to binary, and it's been converted to 128 ones and zeros. In IPv4, we call these octets. There are 4 octets, or 4 groupings of 8 bits, in an IPv4 address. And in an IPv6 address, we have 8 hextets, or 8 groupings of 16 bits, in each portion of an IPv6 address. IPv4 addresses have subnet masks. You can see here we have 192.168.1.100 with a 255.255.255.0 subnet mask. A subnet mask can also be written in slash notation, in this case 192.168.1.100/24. The slash notation only makes sense when you think of the subnet mask in binary. In other words, 255.255.255.0 can be converted to binary, and in binary we can see that it's 24 ones followed by 8 zeros, hence the /24 notation. Subnet masks typically default to /24 255.255.255.0, /16 255.255.0.0, and /8 255.0.0.0. We can see those subnet masks here converted to their binary equivalents. This makes finding the networks and the hosts easy. With IPv4, the ones in the subnet mask define the network. In other words, if we have the host 192.168.1.100 with a 255.255.255.0 subnet mask, the 255s tell us where the network is. It's the 192.168.1 network. The 0 in the subnet mask tells us where the hosts are. In this case, it's host number 100. Similarly, the 172.16.2.33 address has a 255.255.0.0 subnet mask. The subnet mask lets us know that it's the 172.16 network and that this is host 2.33. In the 10.100.100.2 host address, the subnet mask is 255.0.0.0, and this lets us know that it's the 10 network with host number 100.100.2. So looking at the subnet mask in binary, the ones define the network and the zeros define the hosts. With CIDR, or classless interdomain routing, subnet masks can be different than /24, /16, or /8. We could have, for instance, a /26 subnet mask, which would be 255.255.255.192, or we could have a /19 subnet mask, 255.255.224.0, or we could have a /14 subnet mask, 255.252.0.0. There's all kinds of possibilities beyond just /24, /16, and /8. With CIDR, the subnet masks are not so easily defined as /24, /16, or /8. If you take the 192.168.1.0 network /24 and convert the subnet mask to /26, you effectively subnet the network. So instead of the 192.168.1.0 network, you'd now have 4 subnets: the 192.168.1.0 subnet, the 192.168.1.64 subnet, the 192.168.1.128 subnet, and the 192 subnet. Each subnet is a separate network with separate usable host addresses. IPv6 addresses have network prefixes instead of subnet masks. There are no subnet masks in IPv6. So you can see with this IPv6 address, the network prefix is /64. The network prefix tells us how to identify the network. In this case, the first 64 bits of the address, or the 2001:DB8:7AC:1F, defines the network, and the remaining 64 bits is the host identifier. IPv6 addresses are typically presented in a compressed format. For instance, if we look at this IPv6 address, it's been compressed. Let's take a look at it in the decompressed format. In the decompressed format, the leading zeros were omitted. So 2001 DB8 is really 2001 0DB8. And 7AC is 07AC. And the 1F is 001F. And towards the end of the address, the double F is actually 00FF. This is because leading zeros in IPv6 addresses can be omitted. Similarly, contiguous zeros can be replaced with a double colon in an IPv6 address. If we look at this IPv6 address, you can see that there's a string of 6 zeros in a row. This can be replaced with a double colon. The double colon can only be used once in an address. So you can see here in the address, the leading zeros were omitted, as well as the double colon used to replace the 6 zeros in a row before the FF.
In this video, we're going to talk about the fundamentals of number systems. So, in all number systems, the first digit starts with 0. The base of the number system, like base 2, base 10, or we'll see base 16, tells us how many digits are in the number system. For example, decimal is base 10. That means there's 10 digits, starting with 0, 10 digits, 0 through 9. Binary is base 2, 2 digits starting at 0, 0, and 1. Hexadecimal, this is base 16, and it has 16 digits. We're going to look at what those digits are in a moment. The first column is always the number of ones. So this will make sense in just a moment. Each of the following columns to the left of the ones column is n times the previous column, depending on the base of the number system. For example, decimal, base 10 number system. The rightmost column is the column of ones. Because it's base 10, the next column is the number of tens. The column after that is the number of hundreds, 10 times 10. The next column after that is 10 times 100, 1,000, etc. In base 2, the first column of ones. The next column is 2 times that, base 2, so 2 times the previous column, or 2. The next column to the left of that is 2 times the previous column. 2 times 2 is 4. And then we go 2 times 4 is 8, 16, etc. So base 16. Again, the first column is the column of ones. The next column is 16 times that, or 16. Then the next column after that is 16 times 16, 256, etc. Don't worry. We're not going to need to go beyond that, really that first column for what we need to do. But we're going to take a look at both the first and the second column in hexadecimal. Okay, so let's take a look at the hexadecimal digits. Hexadecimal is base 16. 16 digits starting with 0. So let's see what that looks like. On the left there, I have the decimal numbers, 0 through 15. That gives us 16 digits. So let's see what those digits look like in hex. So we start off with 0, then 1, 2. So we use the same first 10 digits, 0 through 9, that we use for base 10 decimal. We use those same digits for hexadecimal base 16. But as you can see, we need to come up with another 6 digits. So what kind of symbols could we use? Well, we could use hashtag, @ exclamation mark, but that's not what we use. It's a lot easier to use a sequence of characters, digits, that we're already familiar with. The alphabet. So let's make 10, that'll be A. 11 B, 12 C, 13 is D, 14 is E, and 15 is F. So to kind of give you an idea of that, if somebody is 10 years old in decimal, we say, oh yeah, we just say you're 10 years old. We use the decimal base 10 number system. But we could easily say you're A years old in hexadecimal base 16. Or when you turn 15, we say you're 15 years old in decimal. We could say you're F years old in base 16 hexadecimal. So you may be wondering, what if I want to go beyond 15? How do I handle that in hexadecimal? So let's take a look at first 8, 9, and some of the simple ones. 8 is 8 in hexadecimal, 9 is 9. We said 10 is A, 14 would be E, 15 F. Now after F, we've run out of hexadecimal digits. But that's okay. So how would we do 16 in hexadecimal? Well, the next column is 16 times the ones column, 16. So we'd have 1 16 and 0 ones. That's the same as 16 in decimal, base 10. Let's look at a couple of other examples. 17 decimal, how would that be in hexadecimal? Well, that'd be 1 16 and 1 1. You just add up the number of 16s and the number of 1s to get the decimal value. 20, what would that be? Let's see, 1 16, and what do I have left over? 16 from 20, that gives me 4 1s. 21, 1 16, 5 1s. 16 plus 5 1s is 21. 26 would be 1 16. Okay, wow. What would we put in the ones column? We have 1 16, so we take 16 away from 26. I've got 10 left over. How do I represent that in hexadecimal? A. So 1 16 and 10 ones. There's our 12, if we want to just represent a simple hexadecimal digit. 29, let's go back up to 29. Let's see, 16. That would be, how many 16s? 1 16. So 16 from 29 leaves me 13. Oh, 1D. Okay, but we really just need to deal with the ones column and what we're going to be working with. So here's a nice chart that shows us the decimal, hexadecimal, and binary representations. So why do we use hexadecimal? Hexadecimal is commonly used in computer science, computer information systems, in representing MAC addresses, Ethernet MAC addresses, and representing IPv6 addresses. The reason is because hexadecimal is perfect for matching any 4 bits. If you notice in our binary here, we have 4 zeros to 4 ones. Every combination of 4 bits can be represented by a single hexadecimal value, because from 4 zeros to 4 ones gives us 16 different unique combinations of 4 bits. So hexadecimal base 16 is perfect for representing this. So 4 bits can be represented by 1 hexadecimal value. 8 bits can be represented by 2 hexadecimal values. So here's a little exercise you can do. You can pause this video and see if you can make these conversions, but using our chart, it's quite easy. So all we have to do is take, in this case, the decimal and find the hexadecimal and binary values. Or take the hexadecimal value, F, and find the decimal and binary. Or the binary and find the decimal and hexadecimal value. Or the binary and find the decimal and hexadecimal value. Here are the answers. So what about 2 hexadecimal digits and converting that to 8 bits? It's very easy. All we have to do is do 1 hexadecimal digit at a time. If For example, 2 is 0010 in binary. A is 1010 in binary. So 2A is 8 bits, 0010 1010. And if you want a little exercise to practice this, try these examples. And here are the answers. So using this little chart, it's very easy to convert between decimal, hexadecimal, and binary. In this video, we're just going to introduce a couple of the differences with IPv6 than IPv4. IPv6 is a very different protocol, and how it conducts business in the network is very different than IPv4. So we're just going to look at 2 examples of those differences. One difference is IPv6 makes use of something known as the link local unicast address. Any IPv6 device must have a link local address. You might notice this link local address when you do ipconfig on your Windows PC or use ifconfig on your Mac or Linux PC. It's an address that usually begins with FE80. So any IPv6 device must have that address, and it gives itself that address automatically. So what is a link local address? A link local address is an address that can only be used on the link. What we mean by link is on that network. It is never routed by the router. It is never sent to another network by the router. So it's contained within that network. The beauty of that is when any IPv6 device starts up, it gives itself a link local address. That means it can talk with any other device on its network using its link local address. It can talk to the printer, it could talk to the router, any device. There are many uses of the IPv6 address that we won't go into detail here, but it is a very important part of IPv6. Another part of IPv6 is how a device can automatically get an IPv6 address and other information like the default gateway address, DNS server address, domain name, and those sorts of things. So in IPv6 world, it all begins with something called the ICMP v6 router advertisement. IPv6, that stands for Internet Control Message Protocol. Okay, so the router advertisement, that comes from the router. It's sent periodically every 200 seconds, or whenever a host says, hey, I need a router advertisement from the router. And it sends what's known as a router solicitation message. It's basically a call out to the network, a message that gets sent says, hey, is there any IPv6 routers out there? Would you send me your router advertisement? We call that a multicast. Okay. The router will then say, yeah, I'm an IPv6 router. Let me send you that router advertisement message. And in that router advertisement message is the addressing information the host can use to create its own global unicast address, its own public IPv6 address, an address that it can use to access any device in the network or any device in the internet. So that DHCP v6 server may not even be needed. So this router advertisement, there's actually 3 options. We're not going to go into detail with these, but I want to explain each of these options. So this first option, you can see there it says SLAC. What does that mean? SLAC stands for Stateless Address Auto Configuration. It just means that the host can create its own address. We say that stateless, meaning nobody's keeping track of assigning addresses. I created my own address. And that's what we mean by stateless address auto-configuration. So there are two other options. Option 2 is this slack with what we call a stateless DHCP v6 server. Wow, what's that, Rick? Okay, so it's exactly like option 1. Basically, it tells the host, says, hey, I can give you all the information you need to create your own public IPv6 address, your own what we call global unicast address. However, there might be some information that I want you to get from what we call a stateless DHCP v6 server. That might be information like the address of a DNS server. So after you create your own public IPv6 address, go talk to that stateless DHCP v6 server and get whatever they have for you, like maybe a DNS address. Now, I said it's called a stateless DHCP v6 server. The reason for that is that server, the DHCP v6 server, is not assigning the host an address. The host created that itself. What it's doing is saying, I'm going to give you information like the address of a DNS server, the same address I give anybody who asks me. So it's not anything particular to you. It's a generic information I'm giving to everybody. Option 3. Now, option 3 is quite a bit different. Option 3 is actually a lot like DHCP for IPv4. This tells the host, says, look, don't use this information in the router advertisement to create your own address. What I want you to do is go talk to what we call a stateful DHCP v6 server. Go talk to a stateful DHCP v6 server who will assign you your address, just like it happens in IPv4 with a DHCP server. The only difference is default gateway information, that address of the router. As you can see that right here, actually, FE80:1, that's a link local address. The router says, I want you to use this address. This is the address I'm sending in the router advertisement. Use that address. That's my link local address. I want you to use that as your default gateway address. That's your way out of the network. But everything else, go talk to that stateful DHCP v6 server. That server is going to give you your public IPv6 address and all the other addressing information you need. Again, like we said, option 1 is the default on Cisco routers and most other routers. And that allows the device to create its own addressing information and everything else it needs without the services of a DHCP v6 server. These are just a few of the differences with IPv6. There's many more, but don't be intimidated. So become familiar with IPv6. It's not that hard. In this video, we're going to take a look at IPv6 address notation. So here we have an IPv6 address. And as you may notice, it uses the hexadecimal number system, 0 through 9, A through F. And if we look at this address, every one of those digits is a hexadecimal digit. So if we take a look at these digits, each digit is actually one hexadecimal digit representing 4 bits. So that first digit, 2, is in binary 0010. This gives us our 128-bit address, but we're representing it using hexadecimal values. So representing an IPv6 address in hexadecimal, we break it up into 8 16-bit segments. So each one of these segments is 4 hexadecimal digits. Each digit, as we saw, is 4 bits. So each one of these 4 hexadecimal segments, sometimes called a hextet, or we just call it a segment, each one of these segments is 16 bits. So we have 8 of these segments. 8 times 16 gives us 128 bits. So that looks like it's a lot of digits to have to write. Well, we have 2 rules to help us reduce the size of writing or representing an IPv6 address. The first rule is omitting any leading zeros in any one of these segments. For example, this first address, we can omit in each one of these segments where we have a leading zero or leading zeros, we can omit those zeros. So we can omit the leading zeros. Let's take a look at another example. We have leading zeros. Those can be omitted. So wherever we see a double colon, and in this case a single digit A, we know there's 3 zeros omitted. Let's take a look at this last example. Once again, any leading zeros in any of the 16-bit segments can be omitted. They do not have to be written. So it's important to know that this rule can only be applied to leading zeros, not trailing zeros. For example, if we allowed trailing zeros to also be omitted, we wouldn't know whether those were leading zeros, trailing zeros, or a combination of both being omitted. It would lead to ambiguity. This case, the only real option is leading zeros. So when we see AB, we have 2 leading zeros being omitted. The second rule is that any single contiguous string of 2 or more 16-bit segments consisting of all zeros can be represented by a single double colon. For example, notice here that we have several zeros in our address. In this segment here, the leading zero can be omitted. In this segment here, the leading zero can be omitted. But we have a contiguous string of 2 or more 16-bit segments right here. That can be represented by a single double colon. So we can write this address as 2001 DB8, omitting the leading zero, double colon, which is representing all these zeros here. 5 contiguous 16-bit segments of all zeros. And that can be represented by the double colon. So using these 2 rules helps us reduce the size in representing an IPv6 address.
In this video, we're going to use Packet Tracer to illustrate how a web page is obtained from a web server. So in this case, we have a PC that is connected through a simulated internet cloud to a web server. And that web server is at www.learnip.com. It also is at the IP address of 172.33.150. So we are going to go out to our PC here, and we are going to request a web page. Now, in order to request a web page, we have to use a client that is appropriate for a web server. So we're going to start out by choosing the web client. And the appropriate client for viewing a web page is a web browser. So we're going to open up the web browser, and we're going to start the capture utility. And then we're going to capture the traffic from the PC0 to the web server. So we're going to put the URL for the learnip.com on the browser, and we are going to request the packet. And you can see that the HTTP packets are being generated and are traveling across the simulated internet over to the web server. The web server is then going to respond and deliver the web page back to the PC. At this point, we are going to stop the capture and take a look at some of these packets. If we examine the packet information by clicking on the box next to the packet we want to investigate, we can see here that it is an HTTP packet, which is generating a web request. It is using TCP as its transport protocol, and it is going to the IP address, the destination IP address of the web server. You can see in this packet that the source IP address is the IP address of PC0. You can also see that when it is communicated, it's initially formatted as an Ethernet frame, and it goes across the Ethernet connection between PC0 and its first hop to get to the internet. When the web server responds, the server takes in that request that it received from the PC0, and then it sends back the response. And as you can see, the response is destined for PC0 as the destination. This process will continue as all information that is related to the web page gets transmitted. In this lesson, we're going to discuss how a web client and a web server use IP protocols to interact. We'll start with the web client side. The web client wants to retrieve a web page from the web server. Okay, the web server is located obviously in a different location, and it has been set up in the standard manner of web servers that it is listening for web requests on port 80, TCP, It's at this IP address, and it's at this domain name, or URL in this case. So we're going to go back to our client, and the client is going to put the URL www.learnip.com on the URL line. As we all know, and we have learned so far, the URL must be translated back to an IP address before the transmission can be sent, because the internet, or any network for that matter, doesn't process the domain names, it processes the IP addresses when it's forwarding and transmitting packets. So when it uses the URL www.learnip, the first thing that has to happen is that a DNS lookup has to occur. A DNS lookup is sending a request to the DNS server in order to get back the IP address that has been associated with www.learnip.com. So in this case, it's going to get returned to it the IP address 172.16.10.50. Now, the IP address is what the packet is going to be addressed to, that's going to contain in its data portion the request for the particular web page, the one in the folder www. So it's done the DNS lookup. Then, once that's completed, the message is going to go to be sent over to the web server. So the second thing that has to happen is there has to be a TCP connection created between the web server and the web client. The TCP connection is going to use the IP address of the web client and the TCP port number assigned to the web client. So in this case, I'm going to give our web client an IP address of 192.168.10.15, and we're going to assign a random port above 1024, so it will be 5507. So the TCP connection will be between the source, 192.16.10.15, port 5507, and the destination, (172.16.10.50), port 80. In communications, this is called a socket. Basically, it is the identifier of all the components that belong in this one conversation, the conversation between the web client and the web server. When the web server receives this packet that comes across, what it's going to do with it is it's going to place it in the buffer assigned to port 80, so that the web service will see that it has a request from this device, and it will then formulate the reply with the opposite information, where the source of the reply is the 172.16.10.50, port 80, and the destination is the 192.168.10.15. And I just noticed I forgot the 8s on this side. There we go. Okay, so we have the 192.168.10.15 and the 192.168.10.15, port 5507. All of the packets that are included in this conversation, all of the web requests and all of the web responses, are going to have this same information, so that this conversation will be able to be identified even as it's traveling through the internet. So various things like routers and firewalls and other devices will all be able to read that these packets are part of the same conversation. In this lesson, we're going to talk about the two transport layer protocols, TCP and UDP. And I'm going to start out with UDP. UDP is a protocol that's used primarily in streaming or real-time communications. And the reason that UDP works best in those types of environments is that UDP is not shackled by a bunch of overhead. And I'm going to explain that in a little bit more detail. At the transport layer, what happens is that communications that is data, which is a large string of bits, and so on. Just imagine how many bits there are in a web page or an email or a streamed movie. And each one of these data segments gets moved down to the transport layer. And at the transport layer, it's broken into segments. And each of these segments gets some port information in the header. So it's from, say, a random port, 5105 as the source. And let's say the destination is a DNS server. So that would be port 53. Each one of these segments is labeled with the source port and the destination port so that they become part of the same conversation. Now, when these actually get transmitted across a network, say like the internet, they may not all go in exactly the same manner. Some of them may get dropped along the way, or they may get put out of order. But in real time, for example, listening to my voice in real time, if we were having an IP phone conversation, if a packet got dropped, we probably wouldn't notice it unless it was a long stream of packets. So basically, for real time, we just allow those packets to take their path from the source to the destination. Say the destination is the DNS server, and for the response to return. We aren't all that concerned about a few packets losing their way or getting placed out of order when they're received, because real time, it's not going to matter, because we're not going to go back and pick up those other things, and the delay to wait would be more disruptive to the communications than losing those few packets. But there are definitely applications where even losing one packet would be catastrophic. For example, in a bank transfer, if we were sending millions of dollars across the internet and we lost a few packets and those happened to be the ones that contained the account numbers, it would be quite upsetting to the people who lost their information. So let's talk now about the other protocol, TCP. When networkers talk about UDP and TCP, they talk about them in terms of reliability. By reliability, what they mean is if packets are lost in a UDP stream, they're not retransmitted, and there's not any worrying going on about whether or not they get there. But in TCP, reliability is built in, not in whether or not any packets get dropped, but in the fact that there's a mechanism that ensures, one, that the fewest number of packets get dropped, and secondly, that if any do get dropped, they'll be automatically retransmitted, that the end user application doesn't have to worry about that. So in TCP communications, we have a source and a destination, just like we did in UDP communications. But each TCP segment has a sequence number in addition to the the source and destination port numbers. So for example, if we were looking at for a web page and we were sending the web page request, we would have a source, again, our random port number, and the destination port number would be 80, which is the TCP port assigned to a web server. So we would then have a sequence number assigned to each one of these segments. This is so that when it gets across the internet to the server, that the server will be able to receive those packets and to be able to account for each one. So for example, if this is 1, 2, and 3, and the server has gotten all of them, it would send back an acknowledgement that wanted me to start with sequence 4. So then I would send the next set of packets along the way. Constant communications goes on between the two devices, and this is the overhead I was talking about a little earlier. Constant communications goes on between the two end devices, the source and destination, to determine how many packets get sent before an acknowledgement comes back. In a very reliable connection, eventually this may be hundreds and thousands of packets. In a very unreliable communications, say for example, across the satellite link going all the way across the world, where there's a possibility for many packets to get dropped, the window of packets that goes before an acknowledgement comes in will get smaller and smaller. This guarantees that the fewest number of packets actually get dropped, because they're being acknowledged much more frequently in an unreliable connection than they would be in a very reliable connection. So the difference between TCP and UDP is that TCP has an acknowledgement of receipt of the packets. And these sequence numbers also allow the destination host to put the packets back in the order in which they were sent. So it has time to get them in the exact order. Whereas with UDP, there's no acknowledgements and no sequence numbers. Each protocol, though, does have its place in communications across the internet, and it's often the criticality of every packet being received that makes the difference whether or not the transmission is sent UDP or TCP. In this lesson, we're going to talk about how transport layer port numbers are used to identify conversations and applications that are the destination and source of transmissions. All right, so let's talk about setting up a server. When we set up a server to provide services over the network, we load applications on that server. For example, a web server application, an FTP application, or a mail transport application. When we set up these services, a port is assigned to them, a transport layer port to the service itself. Now, there are some standard services. Port numbers that are below 1024 are often called well-known ports. And the reason they're called well-known is because they're the most commonly used. For example, a web server listens for communications addressed to port 80. The FTP server to port 21. The mail server to port 25. These and many other well-known ports are automatically identified by the clients. Whenever we open a web browser and we type in a URL, we don't have to tell it what port, because the client, in this case the web browser, already knows that web servers are listening on port 80 to be able to respond to web page requests. So, when our web server is listening, what this means is it has a buffer set up that will accept requests that are addressed to its IP address and also the TCP port 80. If the FTP server is expected to respond, the communications will be addressed to port 21. This enables us to have many different services running at the same time on the web server, so it can be doing many different things. Now, on the host side, host ports for TCP and UDP are dynamically assigned from the range above 1024. And those ports are randomly assigned. So basically, your PC picks one out of the range and it uses it as a source port. So say your web browser is open and you're requesting a web page. The web browser will pick a port, a TCP port. When the traffic goes to the transport layer, the TCP port will be destination port 80 and source from one of the randomly assigned ports. So when the communications leaves the host and heads for the web server will see the destination port as 80. So it will automatically put this request into the queue for the web server to process. When the web server formulates its response, it will respond back with the destination port 5305 and the source port of 80. So when it comes back to the host will know that this is the request that was sent out from the web browser, because the port 5305 was assigned to the web browser request. TCP and UDP ports at the transport layer are what enables our devices to have open many different applications at the same time and have all of those applications communicating simultaneously. Because, for example, if I also had an FTP client running, I could send FTP requests with a different port number. So that would be destination 21 and source port 5307. So then the communications would come back here and it'd go through the same process. Would see that the destination port was 21. It would go in the queue for the FTP server, and when the response came back, it would be addressed to the destination port 5307 so that the host would know that that was the request from the FTP client.
In this video, we're going to introduce the DNS server. DNS stands for Domain Name System Server. DNS server is used to associate a domain name or a host name with an IP address. Let's take a look. Here we have a user that's going to go to the website www.cisco.com. However, the network, the internet, doesn't understand domain names like cisco.com. It only understands IP addresses. So the system needs to associate an IP address with this domain name. So in this case, it's going to ask a DNS server. So the system is going to contact the DNS server and ask it for the IP address associated with www.cisco.com. The query, the question for this domain name goes to the DNS server. The DNS server looks up www.cisco.com, finds the IP address, and then returns this IP address to the host. The host can now use this IP address to contact the web server www.cisco.com, and in this case, download the proper information to display the web page. In this video, we're going to take a look at HTTP and HTML. HTTP stands for Hypertext Transfer Protocol. These are the rules that govern how the information is transmitted between the client, the device asking for the web page, and the web server that sends the web page back to the client. HTML stands for Hypertext Markup Language. This is the coding, the information that actually is used to display the web page itself. Let's take a look. So we're going to start with the client asking for the web page, www.cisco.com. But like we said previously, the network, the internet, doesn't understand names, doesn't understand domain names. It needs the IP address associated with www.cisco.com. So the user, the system, is going to contact the DNS server. The DNS server is going to associate the domain name www.cisco.com with an IP address and return that IP address to the user, to the system. Now the system can contact the web server www.cisco.com using this IP address. This request uses HTTP to request the web page. It is sent to the web server, www.cisco.com, that uses HTTP to return the information, the HTML code, back to the user. Now the user can display the web page, www.cisco.com, in its browser. So here we can see the www.cisco.com webpage. To take a look at the HTML code, we just go right over here to the menu, Developer, click on Page Source. This page source, this is the actual HTML code. This HTML code was downloaded from the web server www.cisco.com to the client system and displayed in its browser. The browser then takes this code, displays it, and we see the web page www.cisco.com. So here we're going to demonstrate how to use an FTP client software. FTP stands for File Transfer Protocol. It allows us to easily copy files from one device to another, from a client device to a server, or from the server back to the client. A lot of times this is used when uploading your web page information to a web server. So let's take a look. Here in FileZilla, where it says host, I'm going to type in ftp.cdc.gov. This happens to be an available FTP server that anybody can use. And the username is going to be anonymous. And there's no password associated with this site. Typically, you're going to have a username and password that's associated with the web server so you can upload and download the information securely. Okay, I'm going to click on Quick Connect. And now we're connected to this FTP server. On the left here is my desktop or the files for my computer. On the right is the remote site. Let me show you how easy it is to transfer a file, in this case from the remote site, the ftp.cdc.gov server, to my local host. So I'm going to go down here, and here we have a welcome message, and I'm just going to drag that over to my desktop, and that's all there is to it. It just copied it from the remote server to my local desktop. And we can actually see that welcome message right here. And there we go. There's the file that we had just downloaded from ftp.cdc.gov. In this video, we're going to demonstrate how to access a server remotely using either Telnet or SSH. So here I've brought up some software known as Terraterm, which allows me to use Telnet or SSH. Telnet and SSH allows me to remotely access a server, another device, as if I was actually sitting at that device. I'm going to use SSH, which is a more secure version of Telnet. So in the host name, I have oslab.cis.cabrillo.edu. This can either be a host name or an IP address. This is the name of a server that I have at school, Cabrillo College, where I happen to teach. So at this point, I have SSH selected. I'm just going to click on OK. It asks me for a username and password. So put in my username, Rick, and I'm going to put in the password. Click on OK. So as you can see, I have remotely connected to this server Opus, which is one of the servers we have at my school, Cabrillo College. So it is as if I am sitting at that computer itself typing in the commands, but instead I'm miles away remotely accessing it.
In this video, we're going to discuss some of the equipment that exists in a typical home network. Most home networks consist of at least two separate networks. The first network is the public network that's coming in from the service provider. Usually in a home, this would be a cable provider or a DSL provider. The DSL provider or cable provider network does not use the same protocols and transmission methods as does an Ethernet network. So the one thing that you're going to see in almost every home network is some type of modem. And what the modem does is it converts the signals coming in from the provider. In the case of this modem, this is a cable TV modem, from the cable television provider. It has an input for the coaxial cable coming in for the cable, and it also has an output port that goes to the local home network. Now, some home networking devices come with the modem built in. As you can see, this one in particular has the connector for the cable company to connect to, and then the outputs are the typical LAN outputs that you would see on a normal home networking device. Now, almost all home networking devices also provide wireless. So once we have our connection made to the outside world, we then have to connect the internet provider to our home network. And you'll notice on this device, it has a yellow port, which is marked internet. Now, one thing you'll notice about all home networking devices, from no matter what vendor they are, is they're typically configured very similarly. You'll notice on this one here, it has an internet in port and also has the LAN connectivity ports. These ports are usually switched ports. On this one, it doesn't require the connection from the modem because it has the modem built in, but it also does have the same network LAN ports that you can attach devices, and it has a built-in wireless access point. Wired ports on a home networking device, and usually these are typically called wireless routers. And the reason that they are called routers is that the ports are separated into two separate networks. The first network is the local network. Then that local network can be either wired, in other words, I can plug in an Ethernet cable and connect it into a device. I can put my standard Ethernet port, and all of those devices will be on the same network. Usually on a home network, wireless devices connect into the same local network as the wired ports. So if you are looking at what the IP addressing is on your home network, you will see that in most cases, the wireless users receive an IP address that is on the same network as the wired users.
In general, when we talk about the cloud, we're talking about three things: data centers, cloud computing or cloud services, and virtualization or virtual computing. Though data centers can be smaller, they're generally large facilities which provide massive amounts of power, cooling, and bandwidth. Only very large organizations like Facebook or Google can afford to build their own private data centers to provide services to their users. Other smaller organizations lease space from a data center. Cloud service providers like Cisco or Amazon Web Services or Microsoft Azure offer their services out of data centers. There are two basic types of clouds: public clouds and private clouds. Public clouds offer services and applications to the general population, whereas private clouds are intended for specific organizations or entities such as governments and are only accessed by those private organizations. There are different categories of cloud services. SaaS, or software as a service, refers to on-demand software or a subscription model where the license and delivery of the software happens through the cloud. You'll find this with things like Office 365 or Adobe Creative Cloud, or even computer gaming software in which access to the software happens typically through a web browser. The software is typically not owned, but rather leased. PaaS, or platform as a service, is where the cloud service provider provides the platform, like the Java or .NET platform for a developer to develop an application or app. This oftentimes involves providing databases and tools to the developer so that they can quickly develop an app. Infrastructure as a service refers to virtual computing that can be provided over the internet on demand. This includes virtual computing such as virtual servers, as well as virtualized storage and virtualized networking capabilities that can be provisioned, allocated, and supplied on demand on an as-needed basis. Virtualization is the ability to abstract or separate the operating system from the physical hardware. To create a virtual computer, the dedicated physical hardware needs to be shared with the virtual computer. In this slide, we see a Windows 7 virtual computer that is sharing the physical dedicated resources of the host computer. This is done through a hypervisor. There are two types of hypervisors used in virtualization: a Type 1 hypervisor, known as a bare metal hypervisor, and a Type 2 hypervisor, known as a hosted hypervisor. A Type 1 bare metal hypervisor is a virtualization server. The hypervisor is an operating system that's installed onto the hardware directly, after which virtual computers can be created. There are different types of Type 1 hypervisors: KVM, Red Hat Enterprise Virtualization, Xen, Citrix Xen Server, VMware ESXi, VMware vSphere, and Microsoft Hyper-V. A Type 2 hypervisor is known as a hosted hypervisor. In this situation, the hypervisor is an application or program that is installed on top of the host operating system. In other words, you install the hypervisor like VirtualBox or VMware Workstation, Parallels Virtual PC on top of the host computer. You install VirtualBox, let's say, on top of the Windows operating system, and then you can create virtual computers. In addition to virtual computing, we can also virtualize switching and routing. In this slide, we can see two VMware ESXi hypervisors. The virtual computers are all networked together with a Cisco Nexus 1000V virtual switch. The virtual switch brings the power of a Cisco switch to the virtualized network environment. Network programming is used to program and virtualize the network. We're talking about protocols, programming, scripting, data modeling, and markup languages, as well as architectures and APIs, or application bases. Protocols like the OpenFlow protocol, which allows a programming language to control the forwarding plane of a switch or a router, as well as netconf and restconf. Programming languages like C, C++, and Java, scripting languages like Python, Ruby, and Lua, data modeling languages like Yang, markup languages XML, and architectures and APIs like the REST architecture and API used over a web browser, and the Java API with all of its libraries and pre-written classes and blocks of code. SDN, or software-defined networking, is an approach to networking where the network is software programmable remotely. It involves the Open Network Foundation, which supports the concept and the development of SDN, and has also been responsible for releasing the OpenFlow protocol or standard, which is a protocol that separates the control plane from the forwarding plane in switches and routers. Also listed here is OpenStack, which is a software platform for cloud computing and providing IaaS, or infrastructure as a service, which means the ability to manage pools of processing power, virtualized servers, and network storage on an as-needed basis for the customer through a data center. In this image, you can see a comparison between a traditional architecture and an SDN architecture. Notice how in the traditional architecture, each device, device 1, device 2, and device 3, let's say they're network switches, each device has a control plane and a data plane. And so to configure those devices, you configure the control plane on each of those devices. In an SDN, or software-defined networking architecture, notice how the control plane has been separated from the data plane, and now the three devices, let's say they're three switches, could be controlled from a single control plane or from a single controller using the OpenFlow protocol. This way, the three switches can be programmed from a single point or a single software program. In this image, you can see this example further. In this case, the application has been developed using Cisco's 1PK Open Network Environment Platform Kit, and the software has been written in, let's say, the C or Java or Python programming languages, and the application can program the data plane on the three switches, device 1, device 2, device 3, using the OpenFlow standard. Network controllers are SDN control plane devices, which are a programmable point of automation to manage, configure, monitor, and troubleshoot virtual and physical network infrastructures. This automates the configuration of the network infrastructure. A network controller is a hardware device which locates the SDN control plane. An example of a network controller used in SDN, or software-defined networking, might be the Open Daylight platform. The Open Daylight platform is an open source SDN controller platform. You can see in this example where the SDN controller works with an application to then control the network devices, here listed as device 1, 2, and 3 at the data plane. The Cisco ACI, or Application-Centric Infrastructure, is Cisco's approach to software-defined networking and network controllers. It involves three main things: an ANP, or Application Network Policy, an APIC, Application Policy Infrastructure Controller, in this case the APEC-EM, which is the enterprise module for APIC, and switches that are application programmable, like the Nexus 9000 series switches. In this example, we can see how the Cisco APEC-EM works. The APEC-EM, or enterprise module, is the SDN controller which sits between the application and policy and the data plane devices, device 1, 2, and 3.
Hello everyone. We want to get some Bluetooth connectivity going here with our computer. Now to do this, there's a couple ways to go about it. There's really like 3 common ways we can go. Now it depends on your Windows operating system, but here in Windows 10, the first thing I can do is click on my Action Center in the bottom right corner, and I can make sure that my Bluetooth is even on, which is Bluetooth and not connected. I can click on that to turn off Bluetooth, or I can click on it to turn it on. I can even right click on it and click on Go to Settings, and that's going to take me to my Bluetooth settings immediately, which is great. But let's go 2 other methods. What I can do in Windows is I can click on the Start button, and I can go to the Control panel, and in the Control panel, I can go to Add a Device, which is inside of Hardware and Sound. And I can add a device including Bluetooth that way. Another way I can do it is I can go to Start, and I can type in Settings, and I can click on Settings. Inside of Settings, I can go to Devices, and in Devices, we'll be here at the Bluetooth settings. Whichever way you prefer, there's multiple ways to get to the same destination. At this point, what I want to do is add a Bluetooth device. So we're going to pause here, and I'm going to turn on my Bluetooth headset. So I've got my Bluetooth headset, and every model will be a little bit different. We're not here to do a video about a Bluetooth headset, but in general, this is the Bluetooth device I'm going to connect. So after researching my device and pulling up the manufacturer's manual for this, I need to put this headset into pairing mode. In pairing mode, it will be able to connect with our computer. So I have the power button here, and there's an indicator light. I can press and hold that power button, and according to my manual, when the light starts flashing red and blue alternating, then it's in pairing mode. There we go. It's red and blue. Now it's in pairing mode, and we can continue by adding it to our computer. Okay. So to continue, the Bluetooth headset is on, and it's going to be in a pairing mode. What I need to do now is click Add Bluetooth or Other Device. When I click on that, it wants to know what type of device I'm going to be adding on. I'm going to click on Bluetooth, because it's going to be an audio device for a headset. So it's looking for the devices. Here it finds some. This is the headset that I have connected that I want to hook up via Bluetooth. I can click on that audio headset, and it's going to connect to it and pair with that headset. The device is ready to go. It says we're connected with voice and music for my headset wirelessly using Bluetooth with my computer. I'll click on Done, and we can even verify this by going back to our Action Center here in Windows 10, and we can see Bluetooth and the name of the device that's connected. If I'm done for the day, I can always turn off my Bluetooth adapter, which will disconnect it from my headset. Also in the future, if I turn on my Bluetooth on my computer, if that headset is nearby, it should be able to connect back to it automatically. And there it is. Bluetooth is on, and the headset is connected again.
In this video, I'm going to introduce you to some important security tips for your home wireless network. It is important to change the default security measures before connecting a wireless router or access point to the network. This includes changing the default SSID, username and password, disabling the broadcasting of the SSID, and for added security, implementing MAC address filtering to only allow specific devices access to your wireless network.
Hello everyone, this is where we get to look at the firewall portion of our Cisco wireless router and firewall combo. Your router should also have some similar features to the ones we are about to demonstrate today. So this router/firewall is connected to the web via the internet board. We can take a look. I'll go ahead and click on status. Takes me to a dashboard. We can see that the WAN port is connected, it's lit up and green. This dashboard can give us a lot of info, including we have a computer connected in off of port 1 of our LAN port. My computer is sitting behind this router firewall on the local area network. This is the inside network, and we will have the ability to configure that inside network and firewall with rules. So this firewall supports a dematerialized zone, a DMZ. This is a subnetwork that is going to be open to the public, but it does exist behind the firewall. A DMZ will allow us to redirect packets going to my WAN port IP address to a specific LAN port device. We'll do that today. We can also set up firewall rules to limit what type of traffic can reach the DMZ so it isn't an open door for all network connections. Let's set it up. We can do it. What we're going to do first is go into networking, followed by LAN. Like we're doing a firewall though. Yes, the DMZ configuration settings on this box are in the LAN area. When I click on DMZ host, we can see here that we get a small amount of options. What we want to do first is we want to actually activate the DMZ. To do that, I'll just go ahead and click on Enable for the DMZ. Next, we need to actually set the host IP address, which is going to be a fixed static IP for the end device that's going to operate in the DMZ. I'm going to change this to 192.168.1.200, which would be the IP address of the end device that should be reachable from the outside world. I'll go ahead and click Save, and it'll save our settings. Next, it would be worthwhile to take a look at some port forwarding settings. That's going to be in our firewall section. So I'll click on Firewall, and we're going to go straight over to Single Port Forwarding. Now, port forwarding allows us to redirect traffic from the internet by looking for specific traffic arriving on the WAN port. We then forward it to a specific internal end device on one of our LAN ports. By default, we can see there's a couple items created for us that are not activated because the Enable button has not been checked, and also there's no internal IP address to forward the traffic to. Now, this is an awesome feature for hosting services on end devices that need to be reachable from the outside. This could be common for accessing internal devices from the outside, such as IP cameras, gaming servers, and more that you'd have on your internal network. What we're going to do is create our own port forwarding rule. I'm going to name mine IPCam1. And with IPCam1 as the name, I will then choose the external port that the people are hitting on the WAN port of my router. So for example, let's say people will be targeting my WAN IP address with a port number of 8090. Then, when traffic is hitting my WAN port on port 8090, we're going to have that target an internal port running on our IP camera device. That internal port on the IP camera device, for example, might be 1044. I would choose the protocol being used by my IP camera. Most likely it'll be UDP based. The WAN interface, I'm going to choose Ethernet. 3G is possible because my wireless VPN router firewall combo does support a 3G cellular data connection for WAN. We don't need that. We'll use Ethernet, which is the WAN port we have plugged in. Lastly, I need to type in the private IP address of my IP camera. This would be 192.168.1.150. I'll make sure I have this rule be activated by clicking the Enable checkbox, and then we'll scroll all the way down to the bottom, and we will click Save. We're good to go. Now we're going to continue on and take a look at some of our basic settings of our firewall. Oddly enough, we're just going to click Basic Settings. I love it. When the screen loads up, what we're going to do is take a look at some of the default security settings that have been set. From the top, we have some anti-spoofing settings in order to protect against internal users that are trying to pretend to be a network device that they are not. That is turned on by default. We also have denial of service protection, which is going to prevent our firewall from being overwhelmed by malicious traffic. We're even blocking ping requests because we're not going to respond to people that try to ping our internet address on our router's WAN port. A bit further down, we can see that our firewall is only allowing an administrator to configure it by using an encrypted HTTPS session. That's right here, called remote access. These remote settings here, if we actually allowed them, would actually allow an administrator to exist outside on the internet and remotely access our router and change the configurations. Now, there are a lot of security settings down below here regarding allowing specific IP addresses to do this from the public side, as well as a port that the WAN port will be listening on. But then again, this is going to be a risky maneuver. So if you do that, be sure you have a very strong password or passphrase. Scrolling down to the bottom, we now are going to take a look at UPnP. UPnP is known as Universal Plug and Play. This will allow automatic discovery of devices that can communicate with the firewall. And the scary part is, if necessary, even modify our firewall to allow for device access from outside the WAN. This would be using features such as port forwarding. Now, while the Universal Plug and Play settings may offer convenience, it's better to set up your own firewall rules and port forwarding yourself. Now, if we want to do some more fine control of what can happen regarding internal traffic, especially stuff that wants to go out to the web, we can. I can go to my Access Rules section, and here I can find this special area where I can add in rows of rules. For example, by clicking on Add Row, inside of here I can choose the connection type, going inbound or going outbound. For example, let's say coming inbound, WAN to LAN. I can have an action. What's going to happen regarding this traffic? Also, we can even set up a schedule for when this should take place, time and day. Regarding services, we can pick what type of traffic. We can even do even more fine-tuned controlling than this using the Configure Services area. Source from what place on the internet could be any. Destination from what place inside my internal network. Single address. We have single address because we're talking about traffic destined for our local area network. This is where we would choose what devices on the internal side should not have traffic arriving to it from a specific public WAN. We're able to activate this rule using our enable button. Also, we're even able to log it, so when this traffic does come through and it is dropped, it will actually be taken note of inside of our wireless router firewall. So what we want to do now is focus more on content, preventing users from reaching specific websites, the inside to outside, but being able to talk content, not just IP addressing like we see here. That's going to be under Internet Access Policy. I'll click on that and we'll head over there next. In Internet Access Policy, I can create multiple policies and activate them on my firewall. I'm going to be able to, let's say, whitelist and blacklist items. Let me show you. I'll click Add Row. And inside of here, we can create a policy name. For example, we can call it Test. And with it being called Test, we then have actions, what to do regarding this policy we're about to create. Block and a schedule, allow and a schedule, always block it, or always allow it. That's called blacklist or whitelist, respectively. Down below, apply access policy to the following PCs. You can choose who this policy is going to be effective for. We can base it off of a range of addresses, a specific IP address, or even hardware level, MAC address. Besides that, when we want to talk about what can we actually block, down below in the website domain name and keyword area, we can click Add Row here, and here you can choose to block based off of domain name or even based off of a keyword that's going to be utilized. Now this is going to be awesome. The reason it's going to be awesome is because this all works together to identify the devices as well as identify what they're allowed to access or not allowed to access. Now with all these settings we've looked at, every firewall will be a little bit different, but the best thing you can do is practice in their configurations and view the result on an internal PC of that network. Make sure you do this outside of business hours and you'll be well on your way to becoming an IT professional.
In this video, we are going to modify a Windows firewall rule. Most firewalls have rules pre-programmed into them that allow them to filter traffic based on different things, like the protocol being used or the source or destination device. In this case, we are going to modify a rule that is pre-programmed into the Windows firewall that denies the PC from replying to ICMP ping requests. So in other words, if you ping a PC with the Windows default firewall settings, it cannot respond to that ping, which sometimes makes network troubleshooting a little difficult when you have a lot of Windows devices. So we're going to go into the Windows firewall settings and create a rule that will permit those pings. To get to the Windows firewall settings, you go to the control panel. So we're going to open the control panel and go to the systems and security settings. We're going to go to the Windows firewall choice and then to advanced settings because we are going to want to modify an existing Windows rule. So basically, I'm going to go into the firewall and I'm going to change the inbound rules. I'm going to create a new rule, which you can see is a menu choice over here. And that new rule is going to be a custom rule. We're not going to take one of the default rules that are available. So we're going to go in and create a custom firewall rule. Our custom firewall rule is going to be based on protocols. The ping request and responses use the ICMP protocol. So we're going to go in and permit ICMP protocol items to connect. So we're going to select ICMP from the drop-down menu. And then we are going to add that rule to our configuration. We're going to take the defaults and we're going to apply it to all of the types of networks that the Windows firewall filters traffic on. We have to give our new rule a name, so we're just going to call it permit ICMP. Now if we look in our firewall rule list, we will see that our permit ICMP rule is now in effect. In order to delete a firewall rule that you've created, find it in the list of firewall rules, click on it, and delete.
In this video, we're going to take a look at the components of an Ethernet switch. Behind the switch here, we have the power cord that plugs into the power supply. In front here, we have some lights. These are the system LED lights. Tells us whether we have power to the switch and some other status information. We have some ports over here. These are the Ethernet ports. This is where we connect the end user systems, the computers, the laptops. This is where we connect routers to the switch. We can connect another switch to this switch, printers, other things. Over here in the corner, we have what is known as the console port. So connected to my computer, I have what's known as a console cable or a rollover cable. This cable here is connected to the USB port on my computer. In the old days, we used to connect these to serial ports. So I have a USB to serial converter that connects the rollover cable to my USB port. And all I need to do is then plug this console cable into the console port. This will allow me to do the initial configuration of the switch, or anytime I want to configure the switch without needing any type of network access. Just physical access to the switch allows me to configure the switch. In this video, we're going to look at how to initially configure the switch, or anytime we have physical access to the switch to be able to configure it. So I've got my Windows 10 machine here, and I'm running some software called TerraTerm. It's known as a terminal emulation software. There's other ones available out there, but I'm going to use TerraTerm. So I'm already physically connected to the switch using my USB cable connected to that serial rollover cable connected to the console port of the switch. So I'm going to go ahead and double click on TerraTerm. So I'm going to choose the serial connection. And because I am using my USB port, I'm going to choose COM3, USB to serial COM port connection, and click on OK. Now, just so that we can see this a little easier, I'm going to go over here to Setup, Font, and I'm going to make sure that we can see this a little easier. There we go. Now, notice I'm not seeing any kind of prompt. Well, that's because the switch has already booted and is waiting for some kind of input from me. It's actually already provided output. I just haven't seen it because TerraTerm hadn't started. So I'm just going to hit Enter. Ah, there we go. It says, would you like to enter the initial configuration dialog? Always say no to this. If you say yes, it will ask you a series of questions that, to be honest with you, will just confuse you. Using the command line interface is much easier to configure the switch or the router. So I'm just going to type N for no. If you accidentally type yes, or if you type yes and you start to do it and you decide you want to get out of that mode, just press Control C. As you can see, I am now at the switch greater than symbol prompt. I am now at the Cisco iOS Internetwork Operating System command line and can start to configure the switch at this point. In this video, we're going to take a look at out-of-band management and in-band management. Out-of-band management requires the computer to be directly connected to the console port of the device, in this case an Ethernet switch. Could also be a router. This allows the technician to access the device without having any kind of network connection. This could be for initially configuring the device, or it could be for troubleshooting the device, or anytime you want to configure the device without having or needing a network connection. In-band management simply means we want to be able to remotely access the device over the network. In this case, our Ethernet switch. So both our Ethernet switch and the device we're using to access it from must be able to communicate with each other over the network. We can then remotely access and configure the device using Telnet, SSH. SSH is much better, more secure than Telnet, or HTTP or HTTPS. So these are the two ways that we can access a device, either out of band management, where we have to have physical connectivity to the device, but no network connectivity, or in-band management, where we can remotely access the device, but we have to have network connectivity to the device.
The process of configuring a Cisco switch can be simulated in Packet Tracer. I'm using Packet Tracer 6.2. The first thing I'll need to do is click on Switches, and then I'll click on the 2960 series switch and place it into the main window. Now I'll need to get a host computer. So I'll click on End Devices, and the first end device is a desktop PC. I'll click on that and then also click in the main window area. So now I have a PC and a switch. To simulate the initial configuration of a Cisco switch, you first need the proper cable. I'll click on the connections icon, and the second connection over is the console cable. I'll click on the console cable, then on the desktop PC, choose the RS-232 serial port, click on it, then drag over to the 2960 switch, click on the switch, and then choose the console port. I now have a connection from the desktop PC to the 2960 series switch using a rollover or console cable. Once you have the serial cable running from your desktop PC to the switch console port, you'll need a terminal emulation program for the initial configuration of the Cisco switch. To do this, you click on the PC, click on the Desktop tab, and these are your desktop applications. The terminal emulation program says Terminal. If you click on it, you'll see the terminal configurations that you would need if you were using a real terminal emulation program like PuTTY or TeraTerm. You can see the bits per second, data bits parity, stop bits, and flow control have already been configured for you. All you need to do is click OK. Now I have a terminal connection to the switch. I'll press Enter to get started, and you can see that I have the switch command prompt available to me. This is how you will need to console into the switches and routers in Packet Tracer skills activities and Packet Tracer exams. For a quick alternative way of reaching a command line interface, you can click directly on the switches and routers, go to the CLI tab, and you can see that it also brings up a command line interface. Furthermore, you can increase the size of the font by going to Options, Preferences, Font, and changing the size of the CLI font. You can see that I've changed mine to 16 to make it easier to read for the video.
In this video, we're going to explore some of the components of a Cisco 1941 router. I'm going to turn the router around to the back because it makes it so much easier to see the different components. The first thing you'll notice is it looks significantly different than the switch did. And the reason is that the switch had many Ethernet ports because the switch provides the connectivity to the access layer devices. Now, a router only connects individual networks. So the router has many fewer ports. So let's take a look at some of them. What you can see here is the color-coded yellow Ethernet ports. Here, these are called Ethernet interfaces. And in this case, they provide gigabit connectivity. So you can see that there are two yellow gigabit Ethernet interfaces on the router. You'll also see a blue color-coded interface, which provides the serial connection for the console cable. The console cable provides the connectivity between the laptop or the computer and the networking device, so that you have a channel over which to communicate to the device for the initial configurations. You'll also notice that there's a mini USB that you can use as a console cable, and there are also some USB ports that you can use to provide additional storage functionality. Otherwise, some of the things are very similar to the switch. You have a power cord connection. Now, a router, you also have an on and off. Many switches come automatically so that when you power them up, they are automatically on, and the only way that you can turn them physically off is to unplug the cable. Now, on a router, it has an on-off switch, so you have to be careful that when you plug it in, that you actually turn the device on. So basically, these are the components of a router as they come out of the box. Now, you'll also notice that the router has something else the switch doesn't have. It has expansion slots. And on this router, you'll notice that there are 3 slots on which you can place additional pieces of equipment. And basically, that's the components of a Cisco 1941 router.
Let's walk through the router boot up process. As you can see, I have a console connection using TerraTerm to a Cisco router. There are 3 major phases. In the first phase, the router runs the power on self-test or POST program. Located in read-only memory or ROM, the power on self-test checks for errors in the hardware like the CPU, the DRAM, and also the NVRAM. After the system posts, the router then runs the Bootstrap program. The Bootstrap program is also located in ROM. This is the end of the first phase. The purpose of the Bootstrap program is to locate and load the Cisco iOS software. The iOS is Cisco's operating system for the router. The Cisco iOS is located, by default, in flash memory. If the iOS image file is not found in flash memory and then loaded into RAM, then the router will look to a TFTP server on the network to see if it can find another iOS image. After the iOS is completely loaded, the router then loads the configuration file, known as the startup config file. This file contains all of the configured settings for the router, such as the host name and interface IP addresses. The configuration file is located in non-volatile RAM, or NVRAM, in the router. If the router cannot find the startup configuration file in NVRAM memory, it will also look to a TFTP server on the network to see if it can find a configuration file. If a configuration file is not located on a TFTP server either, then the router will enter setup mode, which is a configuration wizard meant for initial setup. Let's watch the process in action. I'll go back to my TerraTerm console connection and press return. You can see that I now have a console connection to the router. I'll type enable to get to privileged user mode and then type reload. This will reboot the router and we can watch the boot up process in action. I'll hit enter and proceed with reload. I'll hit enter to confirm. All right, and you can see the system has found the bootstrap. The system has rebooted System Bootstrap version 15. You can see it right there. So the system has performed the post already and now found the bootstrap It's located the memory. You can see there's 512 megabytes of memory on board. There's a DIMM slot that doesn't have any expanded memory in it. You can see that the system has found the ROM-on, or ROM monitor mode, a recovery subset iOS that's located in ROM memory in the event that an iOS is not found. You can see that the Bootstrap program has now found the iOS image file and is decompressing the iOS image. You can tell this from the presence of the hash characters. It's finishing the boot up process. It now recognizes that we are running the Cisco iOS software version 15.2, subrelease 3. At the bottom here, you can see that the memory, the flash memory on the router has been recognized, and now the configuration is being loaded. Now with this router, I've configured one interface, and that is the gigabit 00 interface. So if we look here, I'll scroll up slightly, you can see that the interface gigabit Ethernet 00 has changed its state to up. That's because I've configured it. So we know at this point that the configuration has been loaded, and that's what we see from the output from the router here. At the end now, the router is finished booting, and I can press enter. I'm met with the command prompt.
Let's examine the Cisco iOS command modes. I'll click on PC1, click on the Terminal Emulation Program, click OK, and you can see that I'm presented with a console command line interface. This is the Cisco iOS. I'll press enter on my keyboard to get started. Notice the command prompt at the bottom left of the screen, which indicates the command mode that I'm in. The Cisco iOS uses different command modes to establish various privilege levels for users. Different commands are available in each mode. For instance, the word switch, which is the default name of the switch, with the greater than sign indicates that I'm in user exec mode. User exec mode has very little privileges with access to only a limited number of commands. One of those commands available in this mode is the enable command. At the blinking cursor, I'll type the command enable and press enter, and I'm now in privileged exec mode. I can tell this because the prompt has changed from a greater than sign to a hash or a pound sign. Privileged exec mode offers a higher privilege level for the user and more commands are available. If I would like to go to a higher level, I can go into Global Configuration Mode, or Global Config Mode for short. I can reach Global Config Mode by typing in Configure Terminal and pressing Enter. And now you can see the Global Configuration prompt. This is where most configurations of a switch or a router take place. There are also sub-configuration modes like interface configuration mode. If I type interface VLAN 1 and press enter, I'm presented with a prompt that indicates I am now in interface configuration mode. Many commands will only work from within certain modes. A common mistake made by users new to working with the Cisco iOS is trying to use commands from within the wrong mode. If you are sure that you are typing a command correctly, but you are continually getting an error message, always check your prompt to make sure you are in the right mode. Let's look at the commands that are used to move between the different iOS command modes. We'll look at the enable command, the disable command, configure terminal, exit, and using Control-Z on your keyboard, plus some commands to enter different sub-configuration modes. I have a console connection to a switch, so I'll click on PC1 and press Enter, and it takes me to user exec mode. Notice the prompt at the lower left of the screen. To enter privilege exec mode, I type enable. If I want to return back to user exec mode, I can type disable. I'll type enable to return to privilege exec mode. In order to configure the switch, I need to first get to global configuration mode or global config. I'll type configure terminal, and you can see now that I'm in the global configuration prompt. I can type exit and press enter to return to privilege exec mode. If I type exit again, I leave my console connection altogether. To re-enter the switch and get a command line interface, I have to press enter on my keyboard, and now I'm brought back to the console connection with the switch. I'll type enable and press enter, and then config T, short for configure terminal, and now I'm back in global config mode. Let's enter one of the sub-configuration modes. I'll type line console 0 to get to the management interface for the console port. Now that I'm in a sub-configuration mode, if I type exit, I return to global config mode. This time, I'll type line VTY 0 space 15 for my virtual terminal management interfaces. These are used for remote administrative access to the switch. I can move directly from one sub-configuration mode to another. Notice if I type in interface VLAN 1 and press enter, that my prompt has changed from line configuration mode to interface configuration mode. From here, I can also enter different interfaces, like interface fast Ethernet 0/1. And as long as I don't see an error message that I've typed an invalid command, I'm in interface config mode for fast Ethernet 0/1. I can also move directly to the line console 0. Commands that are normally run in global config mode can also be run from any of the sub-configuration modes as well. If I want to exit out of all sub-configuration modes and return to privileged exec mode, I can use the N command or press Ctrl-Z on my keyboard. Let's give that a try. I'll type end, press enter, enter again, and you can see now that I've returned all the way back to privileged exec mode. I'll return to global configuration mode and then into line console 0. And this time I'll hold down the control key and press Z. And if I press enter, you can see that I'm brought all the way back to privilege exec mode. If I'm in global configuration mode and I type end and press enter, I'm also brought back to privilege exec mode. Learning to navigate efficiently between the different command modes will save you a lot of time.
The Cisco iOS help command is accessed by using the question mark. The help command is context sensitive, so it matters how and where you use the question mark. For instance, let's say I want a list of all the commands that are available to me in user exec mode. I simply type a question mark and I'm returned the commands that are available in user exec mode. If I type enable and enter privileged exec mode and put in a question mark, I'm given the commands that are available to me in privileged exec mode. I'll press the space bar to get the next page of output. An even different set of commands is available to the user in global configuration mode. Notice I'll go to global config mode, put in a question mark, and I'm given a completely different set of commands that are available in this particular command mode. There are other uses for the help command as well. Let's say that I don't want a listing of all of the commands that are available, and I just want help finishing one particular command. For instance, let's say I'm putting in the command interface, but I've forgotten what the complete command name is. I've typed in, and I need help finishing the command. I can put in part of a command, and then put in a question mark, and it'll help me finish the command. Notice that I put in and then a question mark, and the help command has returned that the command that I'm looking for is interface. I can use the help command in another context as well. So now that I know that the command is interface, let's say I'm not sure what the next command parameter or argument is that goes with the interface command. In this case, I'll put a space and then a question mark, and it'll tell me the next parameter or argument that is required by the interface command. Now I know that the next part of the command is either the name of the interface like Ethernet, Fast Ethernet, Gigabit Ethernet, or maybe it's VLAN or range. Related to the help command is the command syntax checker. The command syntax checker will let me know when I have a problem with the command that I've put in. For instance, we can see here that the next part of this command would be one of these arguments here. Let's say I make a mistake and I type in the number 33 instead of VLAN or range and hit enter. Notice that the command syntax checker has informed me that beginning at the number 3, I've made an invalid input. This is extremely useful because it helps me to isolate where the problem is with the particular command that I've entered. This can work in different contexts as well. For instance, let's say that I've put in just the letter I instead of interface and I hit enter. The command syntax checker informs me that the letter I is an ambiguous command. The reason being is that if I type in I and a question mark, there's actually two commands that begin with the letter I in global configuration mode, the command interface and the command IP. The third example of the command syntax checker is when I type in interface and hit enter, and the command syntax checker has informed me that the command is incomplete. To solve this, I put in interface again, a space and a question mark, and I'm given the next set of options that I need to finish this command. You can see how the help command is very useful in learning the different commands that are available to you, as well as the correct context and use of the different commands.
Support for hotkeys and shortcuts makes the Cisco iOS extremely efficient. Making use of these will save you lots of time when you're configuring devices. I have a console connection to a switch, however, instead of using the terminal emulation program to console in, this time I'll click directly on the switch and go to the CLI tab. If I press enter, I'm taken to the command line interface. This is a convenient shortcut to the CLI available to you within Packet Tracer. The first hotkey that I'll talk about is the tab key or tab completion, for automatically completing your commands. You can use it like this. To get to privileged exec mode, I would normally type the command enable. With tab completion, you simply type the first few letters of the command, in this case EN, and press the tab key on your keyboard, and the command is automatically completed for you. This is very useful. Now this will work if only one command begins with the letters EN. For instance, if I want to put in the command configure for configure terminal, and I type CON and press tab, it doesn't work. The command isn't completed. That's because if I put in a question mark, you can see that there's more than one command beginning with the letters CON in privilege exec mode. If I want to use tab completion, I'll need to type CONF and press the tab key, and you can see now the command is completed. For terminal, all I need to do is type the letter T and press the tab key, as there's only one argument or secondary command that follows configure and begins with the letter T, so the switch knows that the command I want is terminal. Even better than using the tab key is command shortening. With command shortening, instead of pressing the tab key to complete the command, you simply use the first few letters of the command, and the iOS will accept the shortened command without hitting the tab key. This is extremely useful. For instance, instead of typing the command interface fast Ethernet 0/1, which is a very long command to type, I can shorten the command to just INT, which is short for interface, F, short for fast Ethernet, and 0/1, and press enter. The iOS automatically knows the command I want and executes it, though you won't see it displayed as you do with the tab completion. Command shortening can make you even more efficient when configuring devices. Sometimes it's necessary to repeat commands. The fastest way to do this is to cycle through your command history using your up arrow and down arrow keys. If I type END on my keyboard and press enter to go back to privilege exec mode, and then I press my up arrow key, you can see that there are two commands in my command history. Pressing the down arrow key will take me forwards in my command history. This is very useful for commands that are used repeatedly. Now let's take a look at some hotkeys. Both Control+Z and Control+C will take us back to privilege exec mode. If I hold down Control+Z and press enter, you can see that I'm back to the privilege exec prompt. Control+C will do the same, and it can also be used to abort certain commands. For instance, if I type CONF and T and then change my mind, I can press Control+C and the command is aborted. Control+A will jump the cursor to the beginning of a line. I'll type configure and then press Control+A, and you can see that the blinking cursor is now back to the beginning of the line. If I press Control+E, the cursor jumps to the end of the line. Control+Shift+6 is another useful key combination. This sequence will interrupt the execution of a command after the command has already been entered. Let's say, for instance, I mistype the command configure and press enter on my keyboard. The iOS is trying to translate the letters that I typed into an IP address. So instead of being stuck in this situation, I can simply press Control, Shift, and 6, and the command is aborted. Lastly, there may be times when you are working on the CLI of a device and an event occurs which generates a message interrupting the command you are typing. This can be very annoying. If this occurs, press Control+R on your keyboard to return to the prompt where the partial command will be displayed, allowing you to finish typing. This sequence is not currently supported in this version of Packet Tracer. I'll simulate the use of these hotkeys by consoling into a physical switch and shutting down an interface on the switch while I'm in the middle of typing a command. I'll press Enter and type Enable to get to privilege exec mode, and then I'll go into global configuration mode. Let's say I want to enter interface G0/1. I'll start typing the command, and now I'll shut down an interface. You can see the message displayed across the screen. If I simply press Ctrl-R, I return to where I left off, and I can keep on typing. Now that's sweet. Using hotkeys and shortcuts is a great way to save you time when working with the Cisco iOS.
In this video, we're going to take a look at some of the basic show commands on a Cisco iOS router. This first command is show running config. What this command displays for us is the current configuration on this router. So this includes all of the commands that have been configured on this router. For example, we have the host name, R1. That gives us this prompt, R1. We have a privileged password. Here is the interface configuration for Fast Ethernet 00 and the IPv4 address. Scrolling down, we can see some other configurations on this router. The interface configuration for the serial 000 interface, its IPv4 address, subnet mask. We can also see that this router has been configured to use the RIP routing protocol. We can also see that the console port has been configured with a password, and we also have configured VTY, Virtual Terminal, Telnet access for this device. The show interfaces command will show us this information or similar information for all the interfaces on this router. The show ARP command shows the ARP table for this router. In this case, it's showing us the ARP table for the Fast Ethernet 00 port. If this router had more than one Ethernet port, it would show us the ARP entries for each of the Ethernet ports that were attached to this router. The show IP route command displays the routing table on this router. The information that it will show is any directly connected interfaces. We can see that with a C. These are the interfaces on this router where the router has an IPv4 address on that interface, and so it's directly connected to that network. We also see R here. R stands for RIP, Routing Information Protocol. RIP is a dynamic routing protocol. The router learned of this route dynamically, automatically from another router. The show protocols command shows information, both global and specific information, for any of our layer 3 interfaces. The show version command displays information about the operating system and some hardware information about this router. For example, it displays the operating system version, in this case 12.4. It also displays information about the interfaces on this router and other information as well, like the amount of NVRAM, memory, and other types of information. These commands and many others can be used to help verify and troubleshoot network operations. There are different variations to each one of these commands. As you develop more skill with using the operating system, you will learn to use and interpret the output of these show commands.